Okay. Example 2, we're going to evaluate from 0, which we don't normally do, but we totally can, all the way to 5 of 2 to the n. So that's going to be 2 to the 0 plus 2 to the 1 plus 2 to the second plus 2 to the third plus 2 to the fourth plus 2 to the fifth. We can talk about combining like terms and like doing this in our head, but we have a calculator. Oh, speaking of, let's use our calculator. TI Nspire, I don't know how to do it with TI-84. TI Nspire, you hit menu and then calculus and then sum. So menu and then 4 for calculus, 3 for sum, and you'll see your sigma notation just kind of pop up there, and then just scroll around and you see blank equals blank, and make sure you use the appropriate variable using your keypad below. Let me see sum for TI-84. This is not going to make your notes any shorter. If you press second stat, which is where the math menu is, it says 5 to select sum. So it is in there. If you go to your math menu, which is in, I hope you all are aware of where your math menu is on your calculator. It's like on the left-hand side of your calculator, if I'm remembering correctly, beneath the like second alpha buttons. So press second stat to get to the math menu, and it says 5 to select sum, and then it will show you the sum. It'll pop up. I'm sorry, TI-84 guys, but if you go onto Google and just say, how do I enter a partial sum, or how do I enter sums into a calculator using TI-84, there will be some happy YouTuber who's like thrilled and wants to show you what they've got going on. Okay, so this is a real challenge to my spatial awareness. Okay, so this is our calculator with the sum in it. I went ahead and plugged it in exactly like that and pressed enter, and it gave me 63. And that is the answer. Ta-da! So your calculator can do it for you. If you end up getting like really, really large sums, if you're asked to evaluate, this is not applied mathematics. This is analytical mathematics. This is math for the sake of math, as opposed to math for the sake of understanding the world around us. So you won't probably on an exam be asked a question like this. It'd be very rare. If you do, you can say, oh, I can definitely just plug that into my calculator, because that's just a calculator question. Okay, so it says write the sum of this guy in sigma notation. This is neither an arithmetic nor a geometric sequence, so writing the formula is a little bit tricky. This is where we have to come up and think about patterns that we see. For our first term, and always with fractions, with rational functions. Remember, a rational function is a fraction function. We always want to deal with the numerator and the denominator separately, because there's two separate things happening on the numerator and the denominator. So just focus on the numerator first and then the denominator. So a sub n equals, looking at the numerator, for the first term, it's 1. For the second term, it's 2. For the third term, it's 4. For the fifth term, it's going to be 5, which means that your numerator is going to be what your number of your term is. That's the relationship. Now, looking at the denominator, for the first term, it's 2. For the second term, it's 3. Third term is 4. Fourth term, it's 5. Fifth term will be 6. Seventh term will be 8. 10th term will be 11. We're adding 1 to the n as we go through in the denominator. So the denominator then is going to be n plus 1, which you could have seen from our, similar to what we had up here above. So that's the definition. Now we want to write the sum. Oh, that's not 5, that's n. But knowing the pattern that we do now, we can see that that is the 99th term of the series. So if we wanted to then turn that into sigma notation, we're starting with n equals 1 all the way up to 99, and then we're going to do n over n plus 1. So we first had to find the definition, the formula for the sequence, by ignoring the pluses and just looking at it individually as terms. And then we had to figure out, well, what was the last term? And we could then compare it to what our formula was. If it wasn't as obvious, you would have to set it equal to a sub n and then solve for n. And then you had to figure out what term number that ends at, which we did with our geometric sequences as well as our arithmetic sequences. And then you take that definition as well as the first term and the last term and put it all together with the sigma. Okay, arithmetic series. When we are talking about a sum of a series, you have two definitions or two formulas that are in your formula packet. They are where your explicit formula is as well. They're just right below it, and it's labeled the sum of n terms of an arithmetic sequence, and it's S sub n, which we saw with our sigma notation up above. S sub n is the sum of a certain number of terms. It only gives you a sum of the first through end number, as in like the first 10 terms or the sum of the first 20 terms. So it looks like the IB with this class will not hold you accountable for understanding how to find the sum of the 5th through the 8th term, right? So you'll only be asked to find the sum of the first so many terms, which is nice because your formula gives it to you in that way. I think it was Einstein, but Einstein's always the answer to the anecdotal things that are going on. But if you're ever asked to find the sum of all integers between 0 and 100, I think it was Einstein. I need to double check. He found this within seconds, and it's because he used the idea of series before it became an idea. If you were to add, let's erase this and do 98, 99, and then 100. If you were to add the first and the last, and the second to last, and the third to last, they will always add up to 101, and it keeps going in that pattern until you get to the middle. So the idea for this is that if you add up the first and the last term to 101 and realize that you're going to be cutting it like that all the way down to a half, then you would be multiplying 101 times half of the total number of terms that you're adding, which is 100. We're adding 100 terms here. So half of that would be 50 because we're cutting it down as we go through the middle. So 50 of those 101s that we added together, you would multiply 50 and the 101, and that's what the sum of all of the digits or all the integers between 1 and 100 are. And that's the formula for your arithmetic series, is that it is the number of terms that you are adding together divided by 2 times the first term plus the last term. There's a second one in there for if you don't know what your last term is. So that's why there's 2 versions of the formula in there. I think either way, this is one I've always taught. And I think it's pretty straightforward on how to find it. Okay. Consider the following arithmetic series, which is 50 terms. It tells you right there that it's going to end at the 50th term. We just don't know what that is. Write the series using sigma notation. We need to know what the definition of this guy is before we can write it in sigma notation. So we need to figure out, is it arithmetic? Is it geometric? It's under the arithmetic banner of these notes. So probably good guess that it's going to be arithmetic. Looking at it, we notice it is arithmetic. A sub 1 is 3, and our common difference is 5, which means our definition is a sub 1 plus n minus 1 times our common difference. Distributing the 5, we get 5n and 3 minus 5, so negative 2. I just distributed the 5 and combined like terms. I just did it in my head really quickly. Okay, so using sigma notation to then talk about that, we're talking about the first 50 terms. So that's n equals 1 all the way to 50 of 5n minus 2. And that's how we write it in sigma notation. Box it, move on. Find the partial sum of the first 50 terms of the series. So I'm going to write down the formula. S sub n equals n divided by 2 times a sub 1 plus a sub n. So S sub 50 is going to be 50 divided by 2 times, and then a sub 1 was 3. And then a sub 50, I'm just going to calculate real quick. 5 times 50 minus 2 is 248. So then add 3 to that, and then times by 25, multiply by 25, and we get the answer of 6,275. Good. Okay. Our last example with arithmetic, and then we'll talk about geometric, and then we're done. I'm sorry, it's so long. An auditorium has 16 rows of seats with 28 seats in the first row, 36 seats in the second, 44 in the third, and so on. So we've got, writing it out, in the first row, 28 plus second row, 36 plus third row, 44, and so on until we get to a sub 16, because there's 16 rows, okay? Trying to figure out what the pattern is here. 28 to 36 is plus 8. 36 to 44 is plus 8. It's arithmetic because we're under the arithmetic banner. We need to find out what is. We have a sub 1. We have the difference, which is 8. A sub n is a sub 1 plus n minus 1 times 8. That's 8n plus 20, 28 minus 8. So then if I wanted to find out what a sub 16 was, I would do 8 times 16 plus 20, and that's 148. So then if I wanted to know what the total number of seats are in this auditorium or in this section of the auditorium, I then now use my sum of an arithmetic sequence formula. S sub 16 is 16 divided by 2 times a sub 1, which is 28, plus a sub 16, which is 148. So 28 plus 148 times 8, which is 1,408 seats. And you're done. That is an application where if you notice a pattern with the first couple of seats, but you don't want to go through and count them all a bunch of times, then there you go.